Okay, children, so classification of magnetic material is the next topic. Okay, classification of magnetic material. So there are basically three categories: diamagnetic material, paramagnetic material, and ferromagnetic material. Okay, now in diamagnetic material, individual atoms, molecules do not possess any net magnetic moment. Okay, on their own. That means they have paired electrons. All in diamagnetic material, the electrons in the atom are paired, so they won't have individual atoms and molecules do not possess any net magnetic moment, because paired electron, one opposite spin, so what will happen, they will cancel each other's magnetic moment. Okay, and if you keep the other property is, if you keep a diamagnetic material in external magnet, suppose you have external magnetic field, here is the external magnetic field, this is uniform magnetic field, okay, equally spaced parallel. Now if you place a diamagnetic material in between, so what will happen, these field lines will go out of it. Okay, so it will be like this. Instead of going from inside as it was before, it starts to move out. Okay, this is the direction. So less number of magnetic field line will pass through it. And I told you that for if we compare susceptibility, so susceptibility for a diamagnetic material is less than 1 and greater than equal to -1. And for a perfectly diamagnetic material, xi is equal to -1, but otherwise susceptibility is between this for a diamagnetic material. Now because susceptibility is this, so mu r, which is equal to 1 plus xi, that will be equal to, it will be between 0 and 1. It's a small number less than 1. Now because it is a small number, so mu is equal to mu r mu naught, if you remember. So that means mu is less than mu naught. Okay, if mu is less than, and magnetism, the constant which we use is mu naught by 4 pi. So you see this will be replaced by mu now, because in the diamagnetic material, okay, you see this will be replaced by mu, not mu naught. So what you will get, mu by 4 pi. So now your mu is less, so that means magnetic field will become less. So magnetic field will become less inside a diamagnetic material. So that's why you see other field lines have moved away. But in when you keep a diamagnetic material, in external magnetic field, okay, so the magnetic field lines passing through the diamagnetic material will decrease. Okay, external magnetic field, magnetic moment in a substance is opposite to external. When you place it in external magnetic field, magnetic moment will in this there will be some magnetic moment. It will show some, if there is some line, even if there is some line passing through it, it will show some magnetic moment in the substance, but it will be opposite to the external magnetic field. Okay, and because it is opposite, so the number of field lines passing through it decreases. Okay, but at the same time, if you have a paramagnetic material, what will happen? So it will show very weak magnetic property. It will show a weak magnetic property in external magnetic field, but the direction, like in case of a, ferromagnet, like a magnet attracts another magnet, here there will be repulsion, there will be slight repulsion. Now paramagnetic material, if you see, okay, individual atoms and molecules in paramagnetic material have non-zero magnetic moment because of unpaired electron. Here the atom or a molecule will have unpaired electron, and because of its spin, individual atoms and molecules have non-zero magnetic moment of its own. So there will be some magnetic moment, and the way they align themselves, that will show slight magnetism, because they will align themselves in a particular direction. Okay, so they will show little magnetism when placed in external magnetic field, otherwise they will not show. So here you see, if same case you have uniform magnetic field and you place a paramagnetic material inside, okay, so what will happen, the magnetic field, the magnetic effect inside the paramagnetic material will be slightly more. Okay, field lines will bend this way as if they are becoming stronger. You see here they were parallel lines, but here they have moved inside more. They are closer here. That means this here inside the paramagnetic material, magnetic field has become stronger. Okay, and if you compare these susceptibility, so here in this case susceptibility is not negative, it is positive. It's a positive number, greater than 0 but slightly less than epsilon. It is less than epsilon, where epsilon is a positive small number. Okay, epsilon is a positive small number, not greater than 1. So it's a very small positive number. So what will happen to mu r, relative permeability? Obviously it will be 1 plus epsilon, and it will be greater than epsilon. Is not that epsilon of electrostatics. This is just a positive small number, and this will be greater than 1. Okay, so it is greater than 1 but not very greater than 1. Positive, great, small, slightly greater than 1. So you see, because mu r is greater than 1, so mu will be greater than mu naught, slightly greater than mu naught. Okay, so that means magnetic field here inside will be slightly greater than the free space. Okay, and it carries, when placed in external magnetic field, it gets weakly magnetized. See, because it's showing stronger magnetic moment, field, so it gets weakly magnetized. It moves from region of weak magnetic field to strong magnetic field. So if you leave this is how it behaves in uniform magnetic field. But if you have non-uniform magnetic field like this, okay, and you place a paramagnetic substance, what will happen? Due to the magnetization, it will move from weak, this is the portion of weak magnetic field, this is strong, so it will move from weak magnetic field region to strong magnetic field region. Whereas in this case, in a diamagnetic material, if you have this kind of a magnetic field, non-uniform, it will behave opposite. It will move from strong magnetic field region to weak magnetic field region. But here it will move from weak magnetic field region to strong magnetic field region. Okay, and magnets repel. If you take a magnet near a diamagnetic material, so it will repel diamagnetic material. Okay, because it has less magnetic field, so it will be repelled. But here it will be slightly attracted. It carries permanent dipole moment of their own. In the absence of magnetization, due to random thermal motion, all the magnetic moment are in random direction, they cancel, so no magnetic field magnetic moment will be there. But when you place it in external magnetic field, all the individual magnetic moment, they align themselves, and then you see that there is slight magnetism in external magnetic field. Okay, in presence of low temperature, now in presence of external magnetic field and at low temperature, it's very important temperature. Okay, low temperature, individual atoms dipole moment can be made to align in a direction, and because of that we have slightly greater magnetic field. If you increase temperature, what will happen? It will lose its paramagnetic property and it will behave like a diamagnetic property. Okay, and then ferromagnetic material. In a ferromagnetic material, there is a concept of domain. Okay, each individual atom individual has a non-zero magnetic moment, just like this, of its own. They interact and align themselves in common direction in a microscopic volume. Okay, what do you mean by that? Suppose you have a substance, this is a substance, a ferromagnetic substance. Microscopic volume are small volumes which are called domain. Okay, small volumes inside it. It's a two-dimensional figure. Volume means three dimension. Okay, so microscopic volume, each microscopic volume is called a domain, and they have their own magnetic dipole. All the atoms inside, their magnetic moment is in one particular direction. So say this. Now in this domain, they all magnetic moment are in one direction. Say this. So each microscopic domain has magnetic moment, but on whole, all these domains are randomly oriented. Their magnetic moment is randomly oriented. So what will happen? There is no net magnetic moment is zero. When you don't keep it in external magnetic field, the magnetic moment on whole is zero. Now when you place this in an external magnetic field, here there is external magnetic field is zero. And when you place it in external magnetic field, same material, now magnetic field is in this direction, say. So what will happen? All these random orientations of small arrows in small domains, they all will align in the same direction. Suppose here is my small domains. Now they all the net magnetic moment of each domain will be in the same direction. Okay, so it is like all in every domain there is reorientation of the magnetic moment according to the external magnetic field, or you can say the size of the domain increases, because all are showing in the same direction. So we can also say that size of the domain increases in the external magnetic field. So now what will happen? It will show a very strong magnetism. Okay, each individual has, okay, it will show very strong magnetism. When placed in external magnetic field, it gets strongly magnetized, and it moves, obviously it will move from a weak magnetic field to a strong magnetic field. So if you have this kind of non-uniform magnetic field, the ferromagnetic material will move from weak region to strong magnetic field region. And if you have to draw these magnetic field lines when you keep it in uniform, if you have this kind of a magnetic field, uniform magnetic field, and you keep a ferromagnetic material, what will happen? Okay, so diamagnetic, this will happen. Paramagnetic, this will happen. Ferromagnetic material may, if you, here I am drawing it, so if you keep a ferromagnetic material, lot of lines will pass through it. Okay, so it shows very strong magnetization in external magnetic field. Okay, and the example, so here susceptibility, if we see, it's much greater than 1. Positive plus very large, this is positive but a small number, okay, near to 0. But here it is a positive number but very large as compared to 1. And mu r will obviously plus 1, if you do, it will be much greater than 1. And mu is also much greater than mu naught. So magnetic field inside will be much greater than the magnetic field in the free space. Okay, now example of a ferromagnetic material. Example is iron, cobalt, nickel, alnico. All magnetic materials are ferromagnetic material. Okay. Then in paramagnetism, if you see the example of paramagnetic material, so here it is iron, cobalt, nickel. Then these are elements. The alloy is alnico. Alnico, this is a compound. It is an alloy of aluminium, nickel, and cobalt. Okay. Gadolinium is also one of the material. Now paramagnetic material, example is aluminium, sodium, calcium, oxygen, and copper chloride, etc. The example of diamagnetic material is bismuth. Okay, bismuth, copper, then lead, and water, NaCl, salt, which we say salt. Okay, now superconductors. If we come to superconductors, it's a perfect conductivity. It shows superconductor means its resistance will be 0. Then it is a superconductor, perfect conductivity. So at low temperature, it is shown. Generally, superconductivity is shown at low temperature. And in labs, perfect diamagnetism, superconductor shows perfect diamagnetism. Okay, in perfect diamagnetism, I told you the value of Xi susceptibility will be equal to -1. Okay, so Xi is equal to -1. And so if Xi is equal to -1, you know that mu r will be equal to 0. And mu will be equal to 0 only then. Because mu is mu r mu naught. So it will become 0. That means if you have external magnetic field and you place a perfect diamagnetic material, all the field lines will go out of it. For a perfect diamagnet, not a single line will pass through it. So it is like a shielding. It will shield this region from external magnetic field. This is called perfect diamagnetism is called Meissner's effect. Meissner's effect is it can be repelled by a magnet, and it can actually shield a space from external magnetic field. Okay, then there is Curie's law, which says that magnetic moment is inversely proportional to temperature. So if I remove this proportionality, it is C B naught by T. Okay, or otherwise susceptibility is equal to C mu naught by T. If magnetic moment C B naught by T, susceptibility C mu naught by T, where C is Curie constant. Okay, and you see its inverse relation with temperature. So more is the temperature, less will be Xi. So it will lose its paramagnetic property. Okay, it will lose. And here in ferromagnetic material, mu is very large. It is of the order of thousands. So it is much greater. Very strong magnetic field is shown here. Okay.